Random forests are some of the most powerful machine learning algorithms available today. So what are they and how are they made? Like a normal forest, random forests are made up of many trees. But in this instance, the trees are decision trees. A decision tree is an algorithm that can be used to perform both classification and regression tasks. It works by sequentially partitioning the dataset based on a series of rules until we have split the data by their independent variables in a way which should be able to predict or classify our dependent variable. So let's look at an example. Suppose we want to predict whether or not to play football based on the weather. Well, first we ask the question, what is the outlook for the day? Either it's sunny, overcast, or rainy. If it is overcast, then we have 4 out of 4 games played, so we can predict that we should play. But if it is sunny, we have just 3 out of 5 games played, and so we can further partition the data to help our prediction. Now if we ask what the humidity is going to be, we can see that if humidity is greater than 70, none of the games are played. Simple, right? But not all cases are that easy. Usually datasets are much messier, which means we need to split our data many times and build a really complex decision tree. The problem is we risk overfitting. This is when random forests come into the party. Random forests employ a technique called bagging, which consists of generating a multitude of decision trees generated from random subsets of the training data and aggregating their predictions. What makes random forests that bit more random, and hence more robust, is that each tree is formed from a random selection of variables. The number of variables selected is approximately the square root of the total number of variables. The aggregation can be done in several ways, but is usually done by voting between the trees, taking the most frequent prediction for classification or the average prediction for regression. This gives us a significantly lower variance without increasing bias. Great, so random forests are clearly some of the most powerful models with a good balance of accuracy and reliability. But random forests are also very popular for their role in model development. In particular, they can be used to identify feature importance. Looking at a single decision tree, important features are located closer to the root of the tree. But looking at a forest of decision trees, we can assess feature importance by taking the average depth of a feature across the model. This can be a very handy way to gain a quick understanding of what features actually matter. Right, so we've heard the pros, but what about the cons? Well, one downside is that random forests do not produce a single decision tree, so they are not as easy to interpret. Another problem is that random forests are complex algorithms with many hyperparameters to tune, such as the number and depth of the decision trees. Getting this right can be difficult. It often requires many iterations and can be computationally demanding. But overall, random forests are some of the most powerful algorithms available to data scientists, having seen application in a wide range of uses from object recognition to molecular biology, and from remote sensing to astronomy. While their use in model development can be applied to almost any data science problem around.